Modern educational technology faces a serious architectural paradox. Institutions demand dynamic, autonomous AI workflows, but they hold highly sensitive learning records that cannot be compromised. Incorporating AI requires massive flows of data, but in education, that stream must be contained to prevent private information from leaking. Platforms must operate under rigorous legal frameworks, like the PDPA in Singapore, the GDPR in Europe, and the CCPA in California. They have to deliver complex AI features while proving compliance with these strict data protection mandates. When raw telemetry or internal model traces leak into a classroom session, they directly expose student identities, learning histories, and private project data. Building a simple wall around the application is no longer an effective defense. User-generated plugins and autonomous agents execute code from within the system, completely bypassing traditional perimeter security. Platforms like LearnAdapt and Critzly manage this tension through a defense-in-depth infrastructure. The architecture is layered specifically to isolate AI processing from sensitive user records. We are going to map this defensive architecture, starting at the bedrock data layer where information first enters the system and moving outward to the boundaries of external subprocessors. In regulated environments, data boundaries cannot be treated as administrative compliance checkboxes. They must be engineered into the platform as strict physical constraints. The entire platform operates on the principle of data minimization. The system collects only the information strictly necessary to provide the service and support the user. Incoming information is instantly sorted into 3 classes: standard account data, AI and app telemetry, and educational data. Learner data automatically receives an elevated classification for maximum sensitivity. Visibility is then locked down, remaining accessible strictly to authorized teachers or administrators. To track student progress, the system processes summarized analytics rather than exposing a continuous stream of raw behavioral tracking data. AI telemetry is routed completely differently. Sensitive student data is explicitly blocked from third-party AI prompts unless a specific, approved use case actively authorizes that connection. The platform also enforces rigid boundaries between processing environments. Research data, pilot programs, and production systems operate in total isolation from one another. By enforcing strict categorization and minimization at the exact point of entry, the architecture heavily restricts the blast radius of any potential compromise. Those categorized data tokens are housed within a physical infrastructure layer, operated entirely on managed cloud services. This perimeter represents the baseline security requirement, demanding mandatory encryption for traffic in transit and at rest across managed cloud storage. Direct database connectivity is restricted, routing traffic through entirely private network access paths for production and staging. File and object storage operate under separate standardized rules. Any internal system attempting to interact with this storage must clear uniform identity-based access controls. Within these storage buckets, a rigid architectural divide separates public-facing assets from private user uploads and generated media. Public access is blocked by default. Creating an exception to expose a file publicly requires explicit review and approval. Even when an exception is granted, there is an absolute prohibition. These public buckets can never contain any system credentials or operational logs or any student data. To guard against accidental data loss, the storage infrastructure relies on automated object versioning as a core component of its backup and recovery planning. This physical hardening guarantees that even if higher-level application logic fails, the underlying data remains isolated, encrypted, and inaccessible. Every interaction with this protected infrastructure is governed by a dedicated identity and access management layer. For human operators, access requires multi-factor authentication. The platform has completely eliminated shared production administrator accounts, tying every action to an individual identity. For machine interactions, internal service accounts operate under the strict principle of least privilege, receiving only the exact permissions needed to execute a specific task. Engineering mandates prohibit the use of long-lived service account keys. Instead, the system handles operational access through dynamic impersonation. This managed secret vault handles database credentials and API keys at runtime, dynamically injecting a temporary credential into a service node only when requested. The system executes automated rotation, instantly invalidating older keys so they cannot be reused. If an exposure is ever suspected, strict incident protocols trigger an immediate manual rotation of all related secrets. Relying on dynamic impersonation and managed vaults ensures that external attackers cannot bypass the infrastructure perimeters by exploiting static, forgotten credentials. The platform also enforces strict controls over the dynamic code and applications generated by users within the LearnAdapt Agentic Studio. These generated plugins are never treated as unreviewed, standalone code. They operate as first-class system components, governed by internal security standards. This pipeline tracks the software development lifecycle. Every AI-generated output package must sequentially pass a mandatory validation gate before entering a staging environment. After undergoing route and runtime smoke tests, it only reaches a production note through tracked release commits. The deployment workflow is paired with strict rollback readiness protocols to instantly revert changes if a deployment introduces system instability. Before reaching users, specific AI governance rules strip all raw telemetry, internal model traces, and secrets from the application output. By subjecting AI-generated agents to the exact same validation gates as human developers, the platform prevents autonomous tools from introducing unvetted vulnerabilities into a regulated ecosystem. An architectural model of this scale requires continuous operational monitoring to detect anomalies in real time. Operational logs are configured with specific monitoring objectives, detecting the public exposure of private resources and identifying unexpected access permissions. Because these logs contain sensitive network metadata, access to the audit trails is highly restricted. When external sub-processors, like cloud hosts or payment providers, interact with the platform, they are contractually bound by strict data processing terms and incident notification limits. Data retention lifecycles are explicitly defined. Information is held only as legally required, and administrators have the tools to execute deliberate deletion requests. Enterprise security is a process of continuous engineering, and the platform's defensive posture is actively evolving. Immediate engineering priorities include further reducing public database exposure, expanding identity-based database access, and continuously refining the validation gates for user plugins. Advanced AI capabilities and strict educational privacy are not mutually exclusive. LearnAdapt and Critzly demonstrate that dynamic intelligence can operate securely when built upon a foundation of zero-trust